Imagine your YouTube, and every day you need to recommend videos from a corpus of billions to billions of users. For over a decade, the dominant approach has been what we'd call large embedding models, where each video gets its own learned vector in a massive lookup table, and the bulk of your model's parameters sit in that table rather than in the neural network itself. This works well for memorizing user-item interactions, but it scales in an awkward direction. You keep growing the embedding table rather than growing the intelligence of the network on top, which is the opposite of what's powered the dramatic gains in large language models, where we scale the network and shrink the input to compact tokens. So the question is, can we adapt the LLM playbook for industrial recommendation and actually deploy it at YouTube scale? That's exactly what the paper called PLUM tries to do. The challenge of bringing LLMs into recommendation is that an off-the-shelf language model knows nothing about your specific catalog of videos or how users behave on your platform. Prior work has explored two main directions. One direction keeps the embedding tables but swaps in transformer architectures to better model user sequences. The other direction, which PLUM builds on, tries to represent each item not as a single embedding, but as a short sequence of discrete tokens called Semantic IDs. Think of it like giving every video a short pronounceable name made of a few syllables, where similar videos share early syllables. Once items are tokenized this way, recommendation becomes a sequence-to-sequence problem the same way translation is, and you can apply all the machinery of language modeling. The seminal work here, called Tiger, trained such models from scratch, but PLUM's bet is that you should start from a real pre-trained LLM and adapt it. PLUM has 3 stages. The first is item tokenization. Each video gets turned into a tuple of discrete code words using a residual quantized variational autoencoder. The idea is, you take a dense embedding of the video, find the nearest code word in a first codebook, subtract it off, then find the nearest code word for the residual in a second codebook, and so on, building a coarse-to-fine hierarchical identifier. PLUM improves this in 3 notable ways. They fuse multiple modalities, things like text metadata, visual content, and audio, by encoding each separately and concatenating before quantization. They use multi-resolution codebooks, where the early levels have many code words for coarse discrimination and later levels have fewer for refining residuals, which makes the SID space more compactly populated. And they add a contrastive loss based on user co-occurrence, so videos that users frequently watch together get pushed towards similar IDs. This last trick is clever because it injects collaborative filtering signal into the IDs without making the IDs depend on volatile popularity statistics that would force constant retraining. The second stage is continued pre-training. They take a pre-trained Gemini model, expand its vocabulary to include all the new Semantic ID tokens, and then continue training it on a 50-50 mixture of user behavior sequences and video metadata. The behavior data teaches the model to predict the next video a user watches given their history. The metadata data, with examples like video with this SID has title X or the topics in this video are Y, grounds the new SID tokens in natural language so they inherit semantic meaning from the LLM's existing knowledge. Remarkably, after this stage, the model retains few-shot text generation abilities while also being able to reason about videos in this new symbolic language. The third stage is task-specific fine-tuning for generative retrieval. Here, the model is trained autoregressively to generate the Semantic ID tokens of videos a user is likely to engage with, conditioned on watch history, user features, and current context. The training examples are weighted by a handcrafted reward signal that captures click quality. At inference time, they use beam search to decode multiple candidate SID sequences and map each back to actual videos in the corpus. A nice property of generative retrieval is that you don't need to maintain a separate item index or do nearest neighbor lookup, and you escape the well-known limitations of dot product retrieval. The results are genuinely interesting. PLUM uses about 100 times more dense network parameters than the production Large Embedding Model baseline, but because it converges so much faster, the total training cost is comparable, actually using less than 0.55 times the floating point operations of the baseline. The 900 million activated parameter mixture of experts model trains on about 250 million examples a day, while the legacy system needs several billion. In live A/B tests on YouTube, adding PLUM on top of an already strong production retrieval system yielded improvements across engaged users, panel click-through rate, views, and satisfaction, with particularly strong gains on shorts where panel CTR jumped nearly 5%. The effective vocabulary size, meaning the number of unique videos needed to cover 95% of impressions, grew by 2.6 times on long-form and over 13 times on shorts, suggesting much better exploration into the long tail. The ablations are illuminating. Running a controlled 2x2 study of whether you initialize from a pre-trained LLM and whether you do continued pre-training, they find both matter and they compound. The pre-trained LLM initialization helps even though the recommendation task feels far from natural language, which they hypothesize is because general sequence processing ability transfers. Continued pre-training dramatically accelerates convergence in the downstream fine-tuning. Their scaling study across models from 110 million to 3 billion activated parameters shows clean power law relationships between compute and both loss and recall, with the optimal model size growing as you spend more compute, mirroring what we've seen in language modeling scaling laws. There are limitations worth naming honestly. The 3 billion parameter model didn't outperform the 900 million one in their experiments, which they attribute to undertraining and hyperparameter constraints rather than a fundamental ceiling. Beam search gives better recall but reduces diversity compared to sampling, which is a real product trade-off. There's a small hallucination rate where generated SIDs don't map to valid videos, under 5% after fine-tuning, but non-zero. And the framework still depends on a heavy upstream pipeline for generating multimodal content embeddings before quantization. They also focused exclusively on retrieval, leaving ranking and personalized search as future work. Now let's walk through some questions you might have after hearing all of this. First, why do semantic IDs help at all compared to just using item embeddings? The key insight is that with an embedding table, each item is an island, a unique vector that the model has to learn from scratch based purely on interaction data. With semantic IDs, items that share content or co-occurrence patterns share token prefixes, so the model can generalize across items the same way a language model generalizes across words that share roots. A new or rare video gets meaningful representation immediately because its tokens are tokens the model has seen attached to similar videos. This is why PLUM dramatically expands the long tail of recommendations. Second, why does starting from a pre-trained LLM help when the task is about video watch sequences, not text? This is one of the surprising results of the paper. The intuition is that LLM pre-training teaches the model very general capabilities like maintaining coherent context over long sequences, learning compositional patterns, and recognizing hierarchies, and these capabilities transfer even when the surface tokens change. The continued pre-training stage then teaches the model that SID tokens behave like a new language with its own grammar, while preserving the underlying reasoning machinery. It's a bit like a linguist learning a new language quickly because they already understand how languages work in general. Third, Doesn't generating semantic IDs auto-regressively at serving time get expensive compared to a single dot product against an index? Yes, it's more compute per request, which is why they use beam search to amortize, and why this is feasible primarily because the network handles small batches of high-value retrieval calls rather than scoring every item. The trade-off they're making is spending more flops per inference in exchange for vastly better sample efficiency during training, escaping the constraints of dot product geometry, and being able to incorporate richer context like text features naturally as part of the prompt. For a platform like YouTube, where retrieval quality directly drives engagement and revenue, that trade-off is worth it. Finally, on how this maps to production recommendation systems at scale. The most directly transferable idea is replacing high cardinality item embedding tables with semantic ID tokenization, even if you don't go all the way to generative retrieval. Hashing SIDs as features in a ranking model can improve cold start and tail item generalization without changing your serving architecture much. For retrieval itself, generative decoding is most attractive on surfaces where you need diverse, context-aware candidate sets and where the existing dot product retrieval is hitting its ceiling. The continued pre-training recipe is also broadly useful because once you've grounded SID tokens in a foundation model, that same checkpoint can serve multiple downstream tasks like ranking, search, and even explanation generation, amortizing the heavy training cost across your stack. The sharper insight for practitioners is the shift in where you spend your parameter budget. The legacy paradigm puts 90+% of parameters in embedding tables and barely anything in the network. PLUM inverts this, and the payoff is faster convergence, better scaling, and a model architecture that can ride the same scaling curves as the rest of modern AI, rather than being stuck in a separate paradigm. For any team running a large recommender, that strategic question of whether your next decade of investment should go into bigger tables or bigger networks is the one this paper forces you to confront.